Hello and welcome to another video. In this lecture, I'm going to continue the discussion on symbolic functions, developing elementary function space for elementary functions. And if you recall, last time we were trying to implement a string representation of the functions and a string representation of the operations between functions. So we looked at the multiplication, and then we also created the subtraction, addition, and division. So let's continue with the addition. So basically, addition implements the addition of two functions and returns a function. So if we have a no arg, if we basically have function f1 f2, okay, and then function f1 function f2, and here this dot f1 equals f1, this dot f2 equals f2, okay. And in order if we want to override the get value, we just get f1 get value plus f2 get value, okay. So get value is easy, and the diff is also easy, f1 dot diff plus f2 dot diff, okay. And then we want to also implement the toString method. So source override implement toString, and in order to basically have the override the toString method, what we are going to do is call, in the simplest form, call the toString method on f1 and f2, okay. But then the question is, what if f1 and f2 are both constant? So if f1 instance of fc and f2 instance of fc, then what we want to do is return new fc with a value on f1 get value, let's say at some point, plus f2 get value at some point, right? So we just want to return a new constant. And if we go to fc, the toString method is basically just a number. Now what happens if one of them is a constant? That's fine. If f1 is a constant plus a function, we prefer to have the function have the constant number on the right side. So we can also test for that. So basically, if we have 2 plus function, we want to convert it to fx plus 2. That makes more sense. So if f1 instance of fc and f2 instance of fc, if f1 is instance of fc but f2 is not an instance of fc, we return basically new addition or we could just return return f2 to a string plus a plus sign plus f1 to a string. Same here, f1 plus a plus sign plus f2, okay. This is the general case. So we can take care of all the possible cases. Two constant function, a constant plus, and then once we implement the addition, we go back to our function and basically take care of in the addition we should also have a public addition. For example, function f1 double v, and then we can similarly have public addition double v function f2, for example. Okay, so if f2 is basically is a double, this dot f1 f1, this dot f2 new fcv, a constant function. Here we have this dot f1 new fcv, this dot f2 f2. Okay, and then in the function we just do the new addition this and v here. So the good thing here is that we are avoiding all these anonymous class implementations. Everything is taken care of in the addition as a separate class, and then we also take care of it makes it more general in comparison to having this anonymous class and just overriding one by one, overriding each method one by one. Return new addition v and this, and here return new addition this and v is a function, and finally return new addition reverse addition v and this. And as you can see, the syntax is basically the same, this v, and he already knows here v is a function, here v is a double. And now we can go and test the addition, test addition, and let's create a main method, and then function f1 is let's from our function space import all the static methods including our variable x. So function space import everything. So here we want to have x, and let's import function. Okay, and then function f2 is sine of x, and function f3 is f1 plus f2, and then system.out println f3. Let's see if this works. X plus sine of x. Okay, and if I do cosine, it works too. Yes, if I do sine of x, it works. If I do for example 2 cosine, also works. Yes, because we already implemented the multiplication for numbers too. And if we have for example sine plus 3 times 2 cosine, so sine plus 3 plus 2 cosine works. And let's make something more complicated. f1 times f2, for example, we can call this f4, function f4 f1 times f2. So summation and multiplication both have been implemented, so we should have no problem having the string representation of our functions. Yes, 3 times 2. As you probably can see here, it doesn't take care of simplification. So and the other thing is that once we have this kind of representation, this representation is wrong because there should be parentheses, right, between sine plus 3 and 2 cosine. So we can go back to our multiplication and maybe just add the parentheses. Let's go here. Sine plus 3 times 2 plus cosine so we should also go into the addition and add the parentheses there. So if we are adding two things together, boom, plus this, and this. Okay, and let's see if this works. Sine plus 3 times 2 cosine works, but we have a little bit of basically parentheses, and the reason we are forced to use these parentheses is because we haven't implemented any method or object that takes care of simplification, that doesn't do the, for example, term by term multiplication. So right now we don't have a term by term multiplication, basically simplifying logic. So we don't have that. So addition and basically subtraction is also very similar. So subtraction, the logic is very similar, extends function, and we just change the name of the constructors. Get value, negative, diff negative. Here we subtract. Okay, and then if I go here and do negative here, this test should fail, not implemented yet. And in order to implement it, we go into the basically function and do the subtraction, new subtract, subtraction this and v, return new subtraction v and this, new subtraction this and v, and return a new subtraction. Okay, and now we can also test it. So if we go here, okay, sine plus 3 minus 2 cosine works fine, and we have to go here too and then do the else if this instance of addition, then we do a return this to basically we do a typecast addition this, and then we do a typecast first and then do the toString. Works and similarly for subtraction, else if this instance of subtraction return subtraction this dot toString. So we're doing typecasting here. Okay, now let's say we have plus. Okay, so let's define function f5 basically f3 dot diff. So diff of plus and multiplication also involves plus and multiplication, so our string method should work. And you see there is one thing here that says not implemented yet. So f1 plus f2. f1 plus f2, we should end up with the cosine, okay, plus 2 times sine. But there is something here that says not implemented. Because in the multiplication we took care of the diff f1 f2 plus f1 diff f2, and so what is this here that it says it's not implemented? And what it is that basically the it's the derivative of cosine is a negative sign, right? And if we go into the cosine, the problem is that we have implemented cosine, but we have not implemented negation. So let's also implement that class negation extend function, okay, and then basically function f, and then public negation, it takes a function f, this dot f equals f, and then get value just negative f dot get value, okay, and diff negative f dot diff, okay. And then for the toString method, return basically negative plus f dot toString. This is the simplest case. And then in the function else if this instance of negation, basically negation this to a string, we have to return this. Okay, and then in the operator overloading for the negation, I am going to do the return new negation this. Alright, now it works. Okay, but again at this point the string representation is not very clean because there is a lot of parentheses around, and the reason for that is that we're not simplifying anything, so it's just a lot of parentheses around. So for example, if you want to evaluate basically f3.div, it's cosine plus 0, okay, plus 2 minus sine, and plus 0 cosine. So it's basically cosine minus 2 sine. That's the diff. Okay, and this was the plus function f6 equals f4.diff, and then sysout f6. So this should also work. Yes, but again the string representation isn't very nice because there are so many parentheses. So in the multiplication, I guess another case that we can implement is basically the fact that if f2 if f1 instance of basically fc, we can check the if we do a typecasting f1 and then get value at some point, let's say 0 or whatever, doesn't matter. If this is 0, so basically math.abs minus 0 basically is less than 1e with some tolerance, minus 1e minus 10 for example, we are going to assume that this function is 0. Okay, so return empty string, because for 0 we don't add or we could add this in the so if we multiply something by 0, it should be 0, so we should return let's say 0. We don't need to return 0 times the function. Let's see, return 0. And the same thing here. If f2 is less than else Yeah, now we get 0. So if 0 is multiplied by a function, it just returns 0. Okay? Alright, so this was the general idea of implementing a function space. I mean, there are also other functions that we can implement. For example, a times x. A times x, we can also implement this, and the reason that it's good to implement this is for this reason. So let's say we have function f7 equals 3.1 times x, and we do a sysout on f7. What we get is 3.1 times x. Okay, and then if we have function f8 is 2 f7, and do a sysout here over f8, it doesn't simplify these numbers, so it just writes 2 times 3.1 times x. But if I define the ax and then try to basically try to implement this, so public ax function f or basically af, a times a function, for example. Right now I'm just trying to implement a times x, and then in the get value we return ax. Okay, in the diff we return a, and when we override the, basically we return a constant function, new fca. Okay, and when we override the toString method, we just do the a times x. Do a, basically a plus times x, for example, something like this. But then in the function, when we look at the multiplication by a number, what we do is that we say that if this is instance of ax, then return new ax of v. Okay, so basically what we are going to do is basically what we are going to do here is that take this number and multiply it by a from this ax function, and then create a new ax. So we get double ax this, we do a typecasting, and then we get basically dot a in the ax. This is private, we just set it to package level access. Okay, and in the function I am able to get a, and then return new ax a times v. Okay, so what happens here, if our function is actually ax, we return a times v times x, for example. Now the same thing for reverse multiplication, the same philosophy applies. So if we get if we have a function a times x, and then we end up with multiplying this with v from the other side, so actually here we end up with for the direct multiplication it's a times x times v, and now we're taking care of this because now a times x times v is transformed into the result of a times v times x, something like that. Okay, so you see the logic here. So these are just the details of how to take care of this, and then in the hierarchy of things we add another else if this instance of ax return typecast ax to this to a string. Okay, let's test this. So the reason this doesn't work because when we multiply this 3.7 times x, it actually returns a function. That's why it doesn't work. Let's say if I write 3.1 times x times 2, does it work? No, it does. It still doesn't work. And the answer is that in the function space, if we look at the function space, we define x as a function, right? And therefore whatever happens to function, so if we want to do this, we have to call x as a x, for example, or maybe ax. Let's define this as ax with a coefficient 1. And let's see what happens here. Okay, now it works. So now x now we have a simplification logic for functions of type a times x. So a times a function a times x, what happens here is that it does simplification. So a times x times b, and remember this simplification was only needed because of the string representation, remember that. So let's see if I put f8, it most likely still doesn't work. No, it works now. Okay, because now x is of type ax. Okay, and then when you multiply it by a number, it's still ax, and we implemented the ax in the overloading, operator overloading for multiplication. Okay, and obviously the next step is that if we have for example do a sysout on 2 sine of x times 3, does this return 6 sine of x? No, it doesn't. It just doesn't have the simplification. So next step is basically having a times any func times b implementing the simplification logic, and we will look into this in the next lecture. Thank you for watching this video, and I'll see you in the next lecture.